Perhaps I will be presenting.
Okay. Good afternoon, everyone. Welcome to Tah Poe Seminar Series 54 and talk number 5.
Not already.
And today our speaker is Dr. Salvatore D. Vincenzo. And today he will tell us about characterizing 1D Klein-Fock-Gordon-Majorana particles. Please welcome our speaker.
Okay, thank you very much. Hello. Okay, super good. Okay, I will be presenting a seminar related to a topic I have been obsessed with. Is about the scalar field, the famous scalar field, and I will be explaining how it's possible a particle could be Majorana at the same time could be Klein-Fock-Gordon. Normally you know this. Okay, you say Klein-Gordon equation, but Fock over there was the reason. I will be explaining this in the seminar. This is, I think, it's a long abstract, but basically I will be showing you these ideas. You can interrupt me if you want, because I prefer to have an interaction with you, because the topic has a lot of mathematical details. And perhaps the seminar is a little bit long, but I had 1 minute per slide, perhaps 1.5 minutes per slide. Okay, theoretically, in 1 + 1 dimension, you can have Klein-Fock-Gordon particles, also in 3 + 1 dimensions. Okay, these are one-dimensional Klein-Fock-Gordon and Majorana particles at the same time. In principle, the wave equation considered to describe such first quantized particle is the standard one-dimensional Klein-Gordon equation. You know the standard. I will be referring to standard Klein-Fock-Gordon equation. Is the standard equation, is second order in time equation, but also you can use the one-dimensional Feshbach-Villars equation. Feshbach is Hermann Feshbach, the saying of the book, the famous book of mathematical methods for physicists. I'm putting here 8 and OR because these two equations are equivalent. You can resolve problem for spin zero particles in 3 + 1 dimension with this equation or also with this equation. But you could put inside the Hamiltonian, in the case of Feshbach-Villars equation, of a Lorentz scalar potential. Lorentz scalar potential, but must be real. And some kind of Majorana condition. In fact, you use the Majorana condition, but perhaps you don't know. In this talk, I will be analyzing entirely and systematically the assumption, the Lorentz assumption, but also I would like to introduce new equations to describe this kind of particles. Yes, something that is perhaps new, but it's not totally new in the Majorana version of wave equations. This equation has not the Hamiltonian form, for example. I call these equations one-dimensional Majorana equation for the one-dimensional Klein-Fock-Gordon particle. Also, you can obtain from each of these equations a second order in time Majorana equation. And finally, I will be discussing the non-relativistic limit of the scalar field, because the scalar field is involved in this equation. Finally, this is Majorana. Perhaps most of you don't know about Majorana because it's not so popular physicist. I just want to present this so you can know a little bit about Majorana. In this date, March 26, 1938, the director of the Institute of Physics at the University of Napoli, this is Naples in Italy, Antonio Carrelli, received a mysterious telegram. That telegram was sent from Sicily, from Palermo, the Sicily Island. It's 300 kilometers in the Tyrrhenian Sea. And in this telegram, he could read, "Don't worry, a letter will follow, Majorana." This was on Saturday. This Saturday, the letter promised reached Carrelli in that, Majorana wrote, I have abandoned suicidal intentions. I will return to Napoli. But it reveals to know him, where could be this guy? Where this illustrious physicist might be. The picture was clearly, Majorana had disappeared. This was 25 March on 1938. Surprised by this circumstance, Carrelli called Enrico Fermi, probably the most important physicist born in Italy, in Rome, who immediately realizes the problem. Fermi, at that moment, was working in his laboratory with Giuseppe Cocconi at the time. Fermi told Cocconi, and this paragraph is incredible. It's one of the things you can feel the importance of Majorana. According to Fermi, Fermi was very tough with his colleagues, just like Wolfgang Pauli. Pauli was also tough. Pauli was the guy that told one day, oh, not even wrong. It's not right. It's not even wrong. Perhaps you know the history of that phrase. So he was very tough with his colleagues. But according to Fermi, you see, told Cocconi, in the world there are various categories of scientists. There are people of secondary and tertiary standing who do their best, but don't go very far. There are also those of high standing who come to discoveries of great importance, fundamental for the development of science. Fermi considered himself to be in this category. But then, according to Fermi, there are geniuses like Galileo or Galilei, his name was Galileo, and Newton. Well, Ettore was one of them. According to Fermi, Ettore Majorana was one of them. Oh my God. Oh, okay, no problem. Majorana had what no one else in the world had. The importance for the physics in Italy, for the Italian physics of Majorana is incredible. We have found a lot of manuscripts with information about theories, about results, mathematical results related to many theories. The name of Majorana is related to many things, not just about Majorana fermions. I will be explaining also that thing. If you want to read more about Majorana, I recommend you this book by Salvatore Esposito. He's working right now at the University of Naples. This book is really good. If you don't have the book, I can give you a copy. Okay, in the introduction, a little introduction, I will be to present the topic, so you are expert in physics, so you can understand the point. We all know this. In 3 + 1 dimension, we have particles with a spin 0 that are equal to its antiparticle. For example, the neutral pion. The antiparticle of the neutral pion is this same particle. I know this is not an elementary particle because the pion, neutral pion, is a hadron. Also, it's a meson. So it's made up of quarks. But it's a fact. So you have that possibility. I will be referring to these particles, neutral particles that are equal to its antiparticle as Klein-Fock-Gordon-Majorana particles. I'm speaking about a spin 0 because I'm considering in the discussion about 3 dimensions, okay? You cannot speak in 1 + dimension about the spin. So there are other things interesting to treat. Okay, recall in general, a Majorana particle is its own antiparticle. So it's a strictly neutral particle. And the wave function that characterizes this particle is invariant under the charge conjugation operation. We know that. All of us knew that within a phase factor. Okay, and but the nose is being 1.5 particles. Just neutrinos could be Majorana. or could be of a Majorana nature, because only neutrinos could be Majorana fermions. We know that. In spin 1, we have photons. The photon and the antiphoton are the same. And the gravitons in spin 2 are also strictly neutral particles. So we can consider this particle of a Majorana nature particle, just because the particle is equal to its antiparticle. Okay, that's my reasoning, my idea in this talk. The wave equation to describe a Klein-Fock-Gordon spin zero particle, as you know, is the Klein-Gordon equation or the Klein-Fock-Gordon equation in standard form. But we need to put, we can put inside a Lorentz scalar interaction and also apply a Majorana condition. We do that because when you are describing this kind of fields or particles, you use real solutions. Because my obsession is, how is possible you can have real solutions of some wave equations? That's the principal topic, the principal idea I will be exploring here. What's the reason I called Klein-Fock-Gordon? Because in this year, 1926, in the same journal, Characterizing for Physics, 3 papers appeared. The first one was Klein's paper. The second one was Fogg paper. And the third one was Gordon paper. So the equation must be called Klein-Fock-Gordon equation, not just Klein-Gordon. On the other hand, the three-dimensional Feshbach-Villars equation, you know, Feshbach, the famous guy that wrote that beautiful book with Morse related to mathematical method for physicists. Perhaps you know that book. But the fact is, Feshbach-Villars proved these 2 equations are equivalent. The standard Klein-Fock-Gordon equation is equivalent to this equation. But also you can put a scalar potential over there. And the respective Majorana condition you can use, but you don't know what is the condition in this case. In the case of a standard Klein-Fock-Gordon, you know, oh, the solution is real. So C is equal to C asterisk. The complex conjugate is equal to that. But what's the reason? By the way, the paper of Feshbach, Hermann Feshbach and Félix-Villars is an old paper, but it's an interesting paper. I recommend you to read this paper. You can learn a lot about quantum mechanics. This is an introduction of the topic because perhaps mostly you know some of these results. Okay, this manner to characterize a three-dimensional particle is the same in 1 dimension, but you cannot speak about spin. The spin vanishes in 1 plus 1 dimension, so we can use the Klein-Fock-Gordon equation 1 plus 1 dimension or the Feshbach-Villars equation in 1 plus 1 dimension. And scalar potential with Majorana condition. Let me do a remark here. Okay, we have spin 0 in 3 plus 1 dimension, but also we can have neutral particles that are not equal to its antiparticles. This is a classical example, the neutral K0 meson. K0 is different to K0 bar. Okay, so the reason is because the strangeness is different in the 2 particles, so different hypercharge, and they can be described by classical complex fields. C is describing this particle, C asterisk is describing the other particle, the antiparticle. So C and C asterisk describe different particles. That's the point. This is trivial, but that's the point. All the quantum field theory and quantum mechanics is based in this idea. Among other things, of course. The other remark is this, but we can have neutral particles equal to the antiparticle, pi 0, for example, the pion. But here we don't have internal attributes. So if you want to describe this kind of particle, you have a classical real field or a real solution of the standard equation. So the Klein-Fock-Gordon equation can have real solutions. And C asterisk describe the same particle because the particle is equal to the antiparticle. Okay, this is a common idea related to this. But we have problems with the idea because we don't have a full-vector current conserving 3+1 dimension. Also, 1+1 dimension is the same. C asterisk equal to C, this is 0. C asterisk equal to C, this is 0. So you get the trivial solution. And if you get this, you cannot obtain a conservation law. This is trivial, you know. But you can change the things because we can find another current, another kind of density to describe the situation. And in the case the field is real, they are not zero, and you can get physics from that. For example, in electromagnetism, you have the same situation. You use A nu, the field is a real vector field, and the current is 0. That's the reason we use the Poynting vector as the current, you know, related to energy. But that's the reason, in fact. And now, because many of you are working in gravitation, there is a big problem here. What is that matter? This is an open problem. In particle physics, we think in particles describing dark matter. There are many particles, but for me, the most important are actions, the so-called actions. According to our observations, the dark matter must be called collisionless, of course. So actions must have a non-relativistic momentum, must have. But we have a problem here because we have a relativistic, massive real scalar field coupled to gravity, and you perhaps need to take the non-relativistic approach. But what is the non-relativistic limit of a real scalar field? What is? It's incredible, but the last 5 years, many papers discussing this situation, this thing, have appeared in many journals, also in the best journals, Physical Review, for example. So we have a problem with the non-relativistic limit of a scalar field. What is? How to obtain that? I present here an example, trivial. What is the non-relativistic limit of the standard Klein-Fock-Gordon equation when the solutions are real? Have you thought about this? Because the books, Rayner books, Messier books, all the books present this discussion, but they consider from the scratch a complex solution. And they took the non-relativistic limit from a complex solution. But how is possible if the solution is real? You cannot use the answer, complex answer. But they used that thing. What's the reason? I pretend to give a response to this problem, How can I overtake the non-relativistic limit of the relativistic Klein-Fock-Gordon real scalar? And finally, in fact, the Schrodinger equation is a complex equation, always. You cannot get real solution of the Schrodinger equation. So the solutions are complex. It's not a surprise. You cannot derive this equation from the Klein-Fock-Gordon when the Klein-Fock-Gordon equation is real. Think about that. Think about it. You have a Klein-Fock-Gordon relativistic equation. The solutions are real, but you need to take the non-relativistic limit. Okay, must be the Schrodinger. Okay, but the Schrodinger equation cannot have real solutions. So what do you do? What do you do in that case? Okay, let me do an intermezzo. Intermezzo is a word in Italian. It's a break. It's a break. Just a break. Because Majorana appeared here throughout the seminar, no? This is the Dirac equation, as you see, no? The free Dirac equation. The operator you have here looks like it's a complex operator because there is an I here and we have the gamma matrices here. But note this, Majorana knows that if this is true, I gamma 0 asterisk equal to I gamma 0 here, the operator is real. This operator could be real when you have this. If you put here another potential, for example, a scalar interaction, the problem is the same. The problem is the same. If you consider a mass depending on the coordinate, it's the same. The coordinate of the time, in fact. Okay, but Majorana found for the first time a set of matrices that satisfy this condition. All the matrices satisfying this condition are called a Majorana representation. You have seen the Majorana representation in books. You don't have a unique Majorana representation. You can have different sets of matrices satisfying this equation, this formula. It's incredible, but Dirac, the creator of this equation, doesn't think about this. Didn't think about this. If this is real, the operator is real, and the solution could be written real. Also, can also be written complex, but can be written real too. Okay, the paper of Majorana appeared in this year, just 1 year before he passed away. Perhaps he passed away because he committed suicide. The teoria simmetrica del positrone it's in Italian the paper. If you want a copy of the paper in English, I can find for you this copy. It's a kind of symmetric theory for electrons and positrons, okay? It's the title. It's a nuovo cimento. It's the new challenge. The new challenge is the name of in English. The particle described by this real solution is what people call Majorana particle. If you have a solution of the latter equation and it's real, it's describing a Majorana particle. Okay. What is a Majorana particle? It's a massive fermion and it's its own antiparticle. So it's a strictly neutral fermion. And now I have a bad news. To date, no elementary particle with speed 1.5 has been identified as a Majorana particle. Many experiments trying to prove the existence of the double beta decay, other experiments, but until now, you can find some objects, some excitations in condensed matter that, and they have a behavior similar to a Majorana particle. The description in that case is in second quantization, but they have not a fermionic statistic. So they are not really Majorana particles. So you can have some excitation in condensed matter that you can consider like a kind of Majorana particle. Also, these kind of particles can be used in quantum computation, in fact. In the Majorana representation, you have the solution is real, as I told you. But in the Majorana representation, this is true. The charge conjugate wave function is equal to C asterisk, just in the Majorana representation. So this is equal to this. So this is the condition that define a Majorana particle. This is the Majorana, the famous Majorana condition, or the invariance of the wave function respect to the charge conjugate transformation, if you want. So when you see this condition, we're speaking about Majorana fermion, or Majorana condition, or Majorana particle, if you want. The concept of Majorana particle comes from fermions, is for particles being 1.5. But you can extend the concept to all the kind of particles. That's what I do. Let me present the mathematics of the most interesting part of the talk. All of you know the Klein-Fock-Gordon equation. This is the Klein-Gordon equation. But we have here a scalar potential, as you know. Look at the equation. A kind of operator here. You can reduce the operator to this expression. Look at the operator. If the electric potential is pure imaginary, this operator is real. Look, because of this I, because of this d squared. So the solution could be real. But also if the potential is 0, you can have a real operator. So in that cases, the solution of this equation could be written real. Obviously, can be written complex too, if you want, but can be written real. This is something I worked many years, I have been working with these kind of things. When the solution of the wave equation is real, and when the solution of the wave equation is complex. But it's a fact. If you don't have an electric potential, you have just a real scalar potential, you can have real solution of the Klein-Fock-Gordon equation. This is not for the Schrodinger equation. Schrodinger is impossible to realize that thing. Okay. Is V, for example, exists and it's not pure imaginary, it's real potential? This is complex. So the solutions are absolutely complex, cannot be written real. That's the point. That's the point. I introduce here these two functions. Just putting this in the latter equation, the standard, you obtain these two equations. These two equations are the Feshbach-Villars equations. If you want, they were able to write this with a Hamiltonian. Yes, the Hamiltonian to describe a particle with spin 0 in 3+1 dimensions. Look at this equation, no? At this Hamiltonian. There are problems with the operator, but we can pass over that problems if you want. Look at this. You have a wave function with two components. The upper component is phi, and the lower is chi. By the way, I will be using the Greek letters, and we'll be using Greek language. For me, it's not phi, it's phi, and this is chi. Okay, and this is psi, not psi. So I will be using the pronunciation in Greek language in this talk. Also, you have here, many of you have seen that formula in relativistic quantum courses. You see this formula, perhaps without S, perhaps without S, yes. This is the famous Feshbach-Villars equation in 1+1 dimensions. And we have a connection between C and the solution of the standard. This C, lowercase, is solution of the standard. And this C is a solution of the Feshbach-Villars. You can prove the total equivalent between the Feshbach-Villars and the Klein-Fock-Gordon equation. Okay, but we have a problem. When C is real, C is every time complex. C is inexorably complex, in fact. Let me do a remark here. It's a theorem. If you have a wave equation of this form, the operator L is real just when this is real. So if AH is a real operator, the solution of this thing can be written real. Obviously, the Schrodinger equation cannot satisfy this formula, so that's the reason you cannot get a real solution for the Schrodinger equation. Okay, I just write construct the charge conjugate of C. You can define this object perfectly. You write the equation for this CC, and you get, after some mathematics, if you want, this equation. Okay, and this equation implies the VC, the transformed potential electric, is minus V asterisk, and the complex on the transformed scalar potential is just S. Okay. For example, if we suppose from the scratch, S is complex, SC is equal to S asterisk. Okay. In this case, this, because I suppose it's a real potential. Okay. And now another remark, simple remark, is because this is quantum field theory, relativistic quantum field theory trivial. This is the case in books, treated in books. When V belong to R, so the potential is real, you don't have, for example, the scalar potential, you have this formula. So this operator with V describes something, and this operator with minus V describes the other. So CC satisfies the equation with minus V, and C satisfies the equation with V. So C describes a particle with a sign of charge, but the other, CC, describe the opposite sign of a charge. So it's antiparticle. So this equation describes a particle, this equation describes the antiparticle. Okay. That's not more complicated to understand. Okay, let's explore the possibility that a Klein-Fock-Gordon particle be its own antiparticle. Okay, I need to introduce a Majorana condition. I put the same Majorana condition as before I explained to fermions. So this condition, and this condition impose restrictions, because in that case, the component of the wave function, the two components, are not independent. You see, if you have phi, chi is phi asterisk. If you have chi, you have phi. Okay, so the components of this wave function are not independent because of the Majorana condition. Just because of that. Obviously, you need to use this also in the equation. So you obtain from that, you obtain this condition. So the potential electric, if you consider an electric potential described in a scalar field, for example, something crazy, but that potential must satisfy this. So it must be pure imaginary. We knew that. We told you, the equation satisfy the operator of Klein-Fock-Gordon is real. Okay, this is the truth. So this is consistent with the hypothesis the solution of the Klein-Fock-Gordon equation are real. Okay? But if V is real, V is zero. So you cannot have a potential here giving us real solution of the standard wave equation. Okay? So it's totally consistent. Let me do another remark here. If we are considering a complex S, in addition to this, we obtain this formula. So we have this and we have this. But, you know, S is real. So no problem. The Majorana condition imposed that S must be a real scalar potential. If you use real scalar potential, it's because of the Majorana condition. The Majorana condition imposed the scalar must be real. That's a fact. And now, this is the equation describing a particle, a Klein-Fock-Gordon particle, that is also one-dimensional Majorana particle. If V belongs to complex, must be imaginary. And if V belongs to it, it's zero. So the scalar must be real. Also, the component of C must be, are connected, because the speed, it's not an S-spinor, in fact, it's just a wave function with two components. This is not an S-spinor, okay? Absolutely not, because the Feshbach-Villars equation is not covariant under Lorentz transformations. But it's not a problem. You can resolve more than you think. I know in the literature, many people don't use this equation to resolve problems related to the Klein-Fock-Gordon equation. But it's interesting. You can have many things from here. Okay, let me do a remark, another remark. Equivalently, you can have this symmetry. The point is the wave equation of Feshbach-Villars is invariant under that. Oh, it's invariant when you change C by CC. And this condition must be true. Oh, that's what we expect to obtain, to get. Okay, so the Majorana condition is related to the invariance of the equation respect to this transformation. That's super good. And the standard Majorana condition, this formula can be written in a vectorial form. It's just this formula. C equal to this. Oh, but this is true, and then we get the famous result. So the wave function of the Klein-Fock-Gordon equation must be real. Must be real. Okay. In fact, you don't read this in books. This is a Majorana condition. When you put the scalar field is real, you're using a Majorana condition, in fact. It's a fact. And also you can obtain the same result using the algebra of the components. So this is equivalent to this. On the other hand, the equation of Feshbach-Villars is equivalent, is invariant, sorry, respect to this transformation. C by minus C, not just C by C, also with minus. And that implies this result. C must be imaginary, pure imaginary. But as we know, this could be written this way. So it's just the function over I. So we can write real, this solution. It's not new physics. not too much new physics, not too much new physics from here. So you can impose this, and also you can impose this. And you can describe a scalar field if you want. Summing up, the Majorana condition appears in two forms. This form appears in this form. In both cases, the solution C of the Klein-Fock-Gordon must be written real, but the potential must be real, the scalar, and imaginary, the electric potential. Okay. The non-standard, I call this standard and call this non-standard Majorana condition, impose all the restrictions. Phi is equal to minus chi asterisk. Remember, the other is imposing this. The standard. And the non-standard is imposing this. Let me do another remark here. It's interesting and important at the same time. Obviously, when you use this Majorana condition, C is an eigenvector of C, the operation of charge conjugation transformation. When you use the other, it's also, but the eigenvalue change in sign. So in principle, the two Majorana conditions describe different particles. Yes, different particles. In fact, for example, the wave function corresponding, you can see this in handbooks, describing the pion is an eigenfunction of C with eigenvalue plus 1, no minus 1. So this is important to see, to consider. Two Majorana conditions, two different of particles describing neutral particles in both cases, of course. Also, we have finally the equation describing how our particle is this equation with these restrictions. When you use this standard Majorana condition, you put this restriction, and you can reduce this equation to this equation. It's easy because C depends on phi and chi. And then you can write chi in terms of the other. So you get this equation. Okay. But also, if you prefer, you can write the equation in terms of chi. And you get this equation. Look at this equation. It's not a Hamiltonian equation because the phi asterisk here. This is a typical characteristic of a Majorana equation. I have studied a lot of Majorana type equations. And every time you try to create, appear this characteristic, the non-Hamiltonian type equation with equation. But it's great. You can find other results from here. So from the Majorana condition, standard Majorana condition, you can get these two equations. Also, V is here. V is here. The electric potential is here. When you use the other Majorana condition, you get another two equations. Look, there are differences. It's plus here in the other case. You see? Plus this. In this case is this. No Hamiltonian equations. Okay? So we don't have equations with Hamiltonian type. Okay, this is just mathematics. And now we need to impose some physics to this problem. Because as you know, the Hamiltonian satisfies this condition. This condition is called the pseudo-hermiticity. So H is in fact, it's a pseudo-Hermitian operator, but it's a formal Hermitian operator, pseudo-Hermitian operator. Is that because this is true? It's because of this condition. You can check this. It's immediately. It's just a matricial relations connected, and that's it. Tau 3 here is the sigma 3 Pauli matrix. So it's not a problem. You need to impose this because this is a property of the Hamiltonian. I will be using a particle inside a box because you have a lot of possibilities related to boundary conditions. But if you don't want to trade a particle in an interval, because this is
Sorry,
true.
the battery is run.
You are
So you
not
have to
hearing me.
check.
Okay. Oh, thank you, T. Okay, so. I'm here, no? Okay. Oh, remember the equation. This is equal to this. Okay, you look at this. But in the real world, the Hamiltonian is a differential operator in the real world. So is this a differential operator? You know what is happening here. The left-hand side is equal to the right-hand side, but you have a boundary term. There are a lot of physics inside this boundary term. Look at the boundary term. It's written in terms of wave function of two components, but also you can write this term in terms of one component wave function, the solution of the standard Klein-Fock-Gordon equation. Okay, this is just a remark, is a technical remark. The last equation is also true. This equation is true with S and V. Just this equation is formally true, even including a real V and S belong to R2, in fact. Okay, this is a technical thing. You cannot reduce this paragraph because it's mathematics. If the boundary conditions imposed on these two wave functions in the ends of the interval, at the ends, must lead to the vanishing boundary term. And so the Hamiltonian H satisfies this. So if this is true, the Hamiltonian is pseudo-Hermitian, formally pseudo-Hermitian, and now pseudo-Hermitian, but must be pseudo-Salaf-joint too. But you can prove this boundary super general boundary condition vanish in the most general way the term written before. This term, you want to vanish this? Okay, you need to use this boundary condition, this big boundary condition. You have a unitary matrix 4x4. Okay, it's not a member of U4 because of this. You have U2, you have 4 real quantities here. These two matrices are the same, so you have 4 parameters, real parameters here, in fact. But you need to impose the reality of the wave function. So that reduces the degrees of freedom of this formula at the same time. You have the matrix. This is technical things. Okay. And finally, you need to impose this because H adjoint is equal to H. When you do this, you are proving, okay, you need to do some things also. It's a pseudo Salaf-joint operator. The Hamiltonian of Feshbach-Villars is a pseudo Salaf-joint operator. It's not just about this, but it is. Okay, you can write the boundary term of the solution of the wave function of the Klein-Fock-Gordon, and also you can prove this beautiful formula. Even you don't have a Hilbert space here, the boundary term is the total derivative respect time of this scalar product. And that's great, because this is 0, this is constant. So you have here a situation in which the norm is, the square of the norm is negative, could be negative, but the scalar product is a conserved quantity, just because the boundary term is 0. This is important property we have here. Okay, I can write also the most general family of boundary condition in terms of the solution of the Klein-Fock-Gordon. This is for Klein-Fock-Gordon, okay? This is the most general family of boundary condition for Klein-Fock-Gordon-Majorana particle. Okay, Klein-Fock-Gordon particle. Where is the Majorana condition here? Okay, you must impose the Majorana condition. In fact, when you have this, you know that this is equal to this. And when you have this non-standard, you have this equality. So C is equal to C asterisk in this case, and C is equal to minus C asterisk in the other case. That reduces the number of parameters you have in the matrix. So the matrix is unitary, but also is symmetric. You prove this. And this condition, together with the other condition, the unitary, you reduce the real parameter to 3 parameters. So this unitary matrix, so the matrix relating the most general family of boundary condition in this problem, when you describe a Majorana particle, when you describe function, a wave function, real wave function, because you have a scalar field, depend on 3 parameters, not 4, because M2 must be 0. So you put here 0, M2, 0, and 2. So you have M0, M1, and M3. But they are related because of this. And finally, you get 2 plus 1. Mu is 3. So you have a general family of 3 parameters, real parameters. This is the most important result related to boundary conditions. And finally, I can give you what is the most general matrix 4x4 is this one. Is this one. So you can work with the Feshbach-Villars solution, or you can work with the other equation, the standard. But also you can play with other equations. I will be showing you. For example, you have here boundary conditions including in our general family. So if you have a Klein-Fock-Gordon particle, and the particle is neutral, strictly neutral, so it's Majorana type, you can impose Dirichlet boundary condition, Neumann. You can impose the Robin boundary condition, periodic antiperiodic boundary condition you want. That's good to know. But also, if you want to describe a Klein-Fock-Gordon but not neutral, you have examples. For example, these 2 boundary conditions are not good for a Majorana particle. You cannot impose this boundary condition if you have a Majorana Klein-Fock-Gordon particle, in fact. So you can describe the situation using just boundary conditions. Okay, we have all the results we need to present the final results, in fact. This is the equation we have because v is equal to 0. So if you create this equation, no Hamiltonian equation, you need to report a general boundary condition for this equation. In fact, I got this general family. This is the most general family of boundary condition for this non-Hamiltonian equation. The most general. And this formula, or this equation, is describing a Klein-Fock-Gordon particle that is Majorana at the same time. This is a real result. I'm giving you the equation, I'm giving you the boundary conditions. Okay, and this is really important, this result. Do you think this equation is difficult to resolve? Perhaps you don't have too much experience resolving non-Hamiltonian equations. Perhaps. I can prove this result. This equation is absolutely equivalent to this equation, so the real part satisfies this, and the imaginary part is just the time derivative of the real part. Phi is complex. Phi is complex. I want to obtain the solution phi, the complex solution. Okay, it's easy. The solution, the real part satisfies the Klein-Fock-Gordon equation. And the imaginary part is just the derivative respect time of the real part. So you resolve this, and the imaginary part is obtained from this, and you get the solution of the equation. So the Majorana equation has a manner, a technique to get us the solution of the problem, of the equation. If you prefer to use chi and not phi, you can do the same. You get boundary conditions, general boundary conditions, and you get equation, and they are equivalent to these equations. Similar, no, they are really similar, in fact, because chi is complex. If you find chi from here, the other component is just algebra. It's chi asterisk. So the problem is really solved. So you can do relativistic quantum mechanics in this situation using just this equation, because the other component of the solution C is just asterisk of the solution of this. This is a really interesting result. Also, you can use the other here the other Majorana. Look, these are the boundary conditions. This equation must satisfy the solution, or this equation must satisfy this. You need to choose boundary condition here if you want to resolve this equation. We're arriving to the most interesting result. This is mathematics, as you see. and reporting the solution of a non-Hamiltonian in terms of the Klein-Fock-Gordon and also one derivative. So simple, right? If you want to work with chi, in the case of the second non-standard equation, you can use this formula if you want. Equivalent to the other. Okay, I call these equations, what equation I call? M4A, M3A, Majorana 2A, Majorana 1A. I call these equations one-dimensional Majorana equation for the Klein-Fock-Gordon-Majorana equation. Sorry, for the Majorana particle. That's what I'm trying to say to you. You can call this because non-Hamiltonian. They are Majorana equations perfectly. They are complex. Depending on Majorana condition you use, the real part satisfies something, and the other is a derivative. So you can use real and imaginary. But this is the procedure to resolve the equation as I show you in this case. Look, if you have the imaginary part, you have the real part that with the derivative. So it's a symmetry. It's a symmetry here. Okay, another new result is this. Each fifth order one-dimensional Majorana equation leads to a second order in time. Yes, you can prove this. For example, the first equation, M1, satisfies also this. Look, it's similar. Phi is complex. And this is not the Klein-Fock-Gordon equation. But you know what? When S is independent of time, this is 0. When the scalar potential is independent on time, it doesn't depend on time, the solution of phi, the second order, is the standard Klein-Fock-Gordon equation. That's great. That's great. So the dependence with time of the scalar potential is important as a condition. Also, you can obtain the other two. So you have 4 Majorana equations first order, and you have 4 Majorana equations second order in time. Time is here. Time is here because it's the energy operator. Time is here. And finally, we are finishing. This I told you already. The second order reduced to the Klein-Fock-Gordon when the scalar potential is what you have. Okay, you don't want to put a particle inside an interval, for example, box. Okay, just make this replacement. The left-hand side of the box is 0 plus. The right-hand side of the box is 0 minus. So this is a point to the right-hand side of the 0, and this is a point on the left-hand side of the 0. So you have, as always, no, you have a particle inside this region, but you can extend the region, and the particle is in all the regions, but not inside this region. Okay, topologically, it's possible to do that perfectly. So you doing or making this replacement is enough. All the results I show you this today are related with this problem too. It's when you want to introduce point interactions, you want. And let me show you about the non-relativistic limit. I will be considering just this because we don't have too much time to present all the limits. What is the non-relativistic limit of this? This is a complex equation. What is? Okay, according to my result, this is equivalent to this and to this. I proved that thing. But look at this. Phi is complex, but the operator is real. So the operator acting on the real part, that is this, is the real part acting on the operator. And you have the real part acting on this. And that's great because phi is complex. You're treating finally with a scalar field, real scalar field, but this part is complex. So you can use the ansatz. This is the ansatz you use when you are trying to get the non-relativistic limit of the Klein-Fock-Gordon equation. You remove MC squared, this part, we're using this, take the first derivative and the second derivative. As you know, these are the conditions for in the non-relativistic regime. If you want, you get this and you get this. If you put this in the equation before presented, you get this equation. This is the non-relativistic limit of my equation. Look, the real part of this. Nobody is saying about phi. Phi is complex. But this is the real part. And this is equal to 0. But this is not exactly the Schrödinger equation. Because the real part 0 doesn't imply C is equal to 0. You see? So this is a big result because according to this, you almost get the Schrodinger equation. In fact, you can get from here the Schrodinger equation, you do something. And that something is the quantum field theorists do when are treating with fields. They consider the independence of the fields. They do this. I will be showing you. Okay, before that, obviously, we have the non-relativistic limit of the equation, right? But we have this and we have this. These two relations are equivalent to my Majorana equation, the two of them. The non-relativistic limit of this is this. But what about the non-relativistic limit of this? Okay, I will be showing you. The non-relativistic limit of that formula is this. But this is always true because the imaginary part of C is always the real part of minus IC. So you don't get any new from here in the non-relativistic limit. And that's great. So all the information you have of the equation of the system is inside this formula. The non-relativistic limit of the Majorana equation describing a Klein-Fock-Gordon equation and Majorana at the same time. Okay, these are the arguments the physicists working in field theory use. In field theory, these two equations are obtained from a Lagrangian, and you suppose that phi and phi asterisk must be varied independently. We teach this to our students. Phi satisfies the Schrodinger equation. Phi asterisk doesn't satisfy the Schrodinger equation because of I, this minus. This equation is not this equation. Because if this equation is this equation, you can write real solutions, but you cannot. So phi asterisk satisfies this equation, and phi non-relativistic satisfies the Schrodinger equation. But you need to suppose phi and phi asterisk satisfy can be changed independently. Just a remark here. Some authors have considered the non-relativistic limit of the standard real Klein-Fock-Gordon. This is the Klein-Fock-Gordon equation you see in books. This C, not phi, C here. In the last 4 years, some physicists have proposed this kind of ansatz and not the normal ansatz to get the non-relativistic limit of the scalar field. The Klein-Fock-Gordon, in the case C is real. Okay, but this is real because this is proportional to the real part of this thing. So they are proposing this real, and they use this ansatz. Okay, if you put this inside this equation, you take this and you put this here, you get the Schrodinger equations when you take this limit, the non-relativistic, and you assume there are independent fields. On the other hand, to finish, if you do the same in the Lagrangian, you get a lot of terms like this. And all people reduce it to zero. They ignore this fast oscillating term. This is a really big frequency here. But that condition, you don't have a real reason to remove that term. I haven't found that thing in the real world. So we have a problem here. The problem exists because people working with the actions are treating to reduce a relativistic real field to a non-relativistic real field. Oh, how is possible? Because the solution of the Schrodinger equation must be written complex every time. So finally, my equation, my non-relativistic limit, this. Do you want to get the Schrodinger equations from here? Okay, just suppose phi and phi asterisk are independent. If you do this, you get the same result people obtain normally. This result. My equation generated the equation of equations. If you suppose this are independent fields. But this is This is not trivial. It's not trivial. So no trivial in the last 5-6 years, many physicists have contributed with results, and there is not a consensus related to this. There is no unique conclusion related to this. Finally, just the last, we can have and describe particles, this kind of particles, using our equation, Klein-Fock-Gordon and Feshbach-Villars equation. We have two types of Majorana conditions. Both Majorana determine the scalar potential must be real. That's the reason. And the electric potential must be zero. If you put this in an interval, you get the most general condition, boundary conditions, for the solution, the real solution. And finally, the latter two general set of boundary conditions are the same for the two types. So it's interesting, but we have two boundary Majorana conditions, but you have the same sets of boundary conditions. They don't depend about the Majorana condition. It's interesting. Finally, because of the Majorana condition, the complex components of the wave function are not independent. So we can write Fields equations, and that's it. This is the principal point of resolve this talk. The problem is that they don't have a Hamiltonian form, but they can reduce to a real Klein-Fock-Gordon equation you can resolve, and then with a derivative, you resolve the problem. And also you can write complex second order in time. These are complex equations, especially when the scalar interaction depend explicitly on time. And finally, the non-relativistic limit, one of the first order Majorana equations, can lead the Schrödinger equations. But just when phi and phi asterisk are assumed to be independent fields. I was trying to write in Thai Kapkum, but I got problems with my latex. I don't know how to write Kapkum. So Kapkum, to all of you have been here. Thanks very much, and grazie mille per essere qui, and gracias.
Okay, thank you very much for a nice talk. So if there are any questions, please feel free to ask. If there are any questions.
I have here the slides. If you have a question, we can look for the page, and we can. I want to say something more. Here inside the IF, we have meetings, internal meetings. As you know, we have Pichet's meeting. Pichet is a professor here at the IF. And in the last meeting, Pichet's meeting, I will be showing you some details about this talk. I think it's pertinent to do that. So, we have some questions.
Okay, we have some question from the audience online.
Oh, okay.
So the first one is it have something to do with topological quantum computing?
Oh, okay. Yes, but this is not a Majorana particle. In fact, they have a behavior similar, but they are not a real elementary particle. No. You can have some excitations in condensed matter, and when you treat this problem in second quantization, you can get similar result or related to types of Majorana condition inside the structure of the theory, and they are proved to be interesting. So I can tell absolutely it's true. We can make a Majorana particle, a kind of in some kind of solid state system. But my interest is in elementary particles, okay? High energy situations, okay? Not in this particular situation, but yes, they are supposed to help to create many things in quantum computation. Yes, Majorana particles, yes.
Okay, and the second question is, why is it bad for not having Majorana particle as an elemental as an elementary particles. Is it bad?
Yes, it's really bad.
And
Because
what
according
is
to the standard model, that they are really whale particles. That's the reason we put all other things, physics beyond the standard model. So we need to put other things. Yes. Nobody knows. Until now, we don't have the presence of a Majorana particle, a Majorana fermion in the experiment, trying to prove the reality of the double beta decay, the beta decay. And that's the problem. Until now, we don't have. But it would be great if we find a kind of particle. Fermions is strictly neutral. Fermion is strictly neutral. That's a Majorana particle. That's a Majorana fermion. But we don't have it right now.
okay? So the main candidate would be neutrino, but it's still debatable.
Yes, many years working in that, and many physicists working in that topic is. My principal interest is the mathematical structure of this equation, web equation trying to describe situations related to neutral fields, because my obsession is neutral fields. So when you can obtain real solution of wave equation, what are the conditions you need to impose to get this? I proved in this talk you can do that thing when you have particles. Type Klein-Fock-Gordon, type Majorana, yes, of course. But we don't have spin in one plus one dimension, in fact. The spin is just in 3 plus 1 dimensions, okay? That's important to clarify, to precise, yes, in fact.
Okay, thank you very much. If there are further questions? Okay. If everyone don't have questions, okay, let's say thank you to our speaker.
Thank you very much for the opportunity.
And I would like to announce that there is the next Tah Poe Seminar after your talk, and the speaker is our PhD student, Alberto Maya Perez. Thank you. Okay.
Thank you.